Welcome to Talk 9. We've already covered Kaplan-Meier survival curves in Talk 3 and logistic regression in Talk 5. Today we're combining those two worlds, time to event outcomes, with multivariable adjustment by tackling Cox proportional hazards regression. Cox regression is the most commonly used method in veterinary oncology and cardiology papers for identifying which clinical factors independently predict survival, relapse, or other time to event outcomes. It produces adjusted hazard ratios, a metric that many clinicians confuse with odds ratios. By the end of this talk, you'll know exactly what a hazard ratio means, how to read a Cox regression results table and forest plot, and how to spot when the key assumption of Cox regression, proportional hazards, might be violated. Let's get into it. Here's our roadmap. We'll start with why Kaplan-Meier alone isn't sufficient when patients differ in important baseline characteristics. Then we'll build up the Cox model from the concept of hazard rates, cover the critical proportional hazards assumption, and read a real results table and forest plot. We'll close with the odds ratio versus hazard ratio versus risk ratio comparison that trips up so many readers, and then we'll apply it all to a clinical case. Start with the problem Cox regression solves. In a non-randomized survival study, say a retrospective study comparing two chemotherapy protocols, the two groups may differ systematically. One protocol may have been preferentially given to younger dogs or to those with earlier stage disease. If you just plot the Kaplan-Meier curves, you can't tell whether the survival difference is due to the treatment or to those baseline differences. Cox regression fixes this by simultaneously modeling all the relevant covariates, age, stage, weight loss, neutrophil count, and producing an adjusted hazard ratio for each one. The adjusted hazard ratio for treatment tells you, holding age, stage, and all other variables constant, what is the independent association of this treatment with survival. This is exactly the same logic we applied in logistic regression in Talk 5, but now we're doing it for time to event outcomes instead of binary ones. Hazard rate is the conceptual engine of Cox regression, and it's worth understanding intuitively. Imagine you're watching 100 dogs with lymphoma. At month 6, you observe how many die in that specific interval. That rate of dying per unit time among those still alive is the hazard rate at month 6. The hazard rate can change over time. It might be high early in a disease course and then level off, or it might rise steadily as disease progresses. The left panel of the figure shows these different hazard shapes. The hazard ratio is then the ratio of this rate between two groups. HR equals 0.55 means the treatment group's hazard rate is 55% of the control group's hazard rate at any given moment. They're dying or relapsing at roughly half the rate. If the curves never cross, this ratio stays roughly constant over the whole follow-up period. Key assumption of Cox regression, and it's the one most commonly violated without being flagged. The proportional hazards assumption says that the ratio of hazard rates between groups stays constant over the entire study period. Visually, the Kaplan-Meier curve should maintain roughly the same separation from start to finish. If the curves cross, one treatment is better early and the other better late, the proportional hazards assumption is violated, and a single HR is averaging over two opposing effects. We covered crossing curves briefly in Talk 3, but now you understand the mechanism. The Shinfield residuals test is the formal statistical check. If it gives p less than 0.05, the assumption is likely violated. When you read a Cox regression paper, check, do the KM curves cross? Is the failed test reported. If neither is addressed and the curves cross visually, treat the reported HR with caution. The Cox forest plot uses identical skills to the logistic regression forest plot from Talk 5. The key difference is the output, hazard ratios, not odds ratios. HR below 1, treatment in this example, is protective. HR above 1, late stage disease, weight loss, signals worse prognosis. The log scale is essential here. Without it, the protective effects would be squished between 0 and 1, while harmful effects would spread out toward infinity, giving a visually misleading impression. Always check. How many events were there? The rule of 10 from logistic regression applies here too. You need approximately 10 events per covariate in the model, and confirm these are adjusted HRs, not crude ones. The most common source of confusion when reading veterinary survival and outcome studies, so let's be very explicit. All three metrics, OR, RR, and HR, compare two groups, and all three equal 1 under the null of no difference, but they measure fundamentally different things. The OR compares odds, the RR compares probability, the HR compares instantaneous rates over time. When events are rare, under 10%, all three converge to approximately the same value. This is why early survival papers sometimes reported ORs from logistic regression, even for time to event data, and got away with it clinically. But when events are common, or when the study follows patients for a long time, the OR exaggerates the effect compared to the RR, and neither the OR nor the RR properly handles the time dimension the way the HR does. The take-home: identify the statistical model first, then interpret the output appropriately. Let's work through this case. Complete surgical margins, adjusted HR equals 0.42, CI 0.26 to 0.68, P less than 0.001. CI doesn't cross 1. Achieving complete margins reduces the hazard of death by 58%. This is the strongest protective factor in the model. Tumor grade, HR equals 2.15, CI 1.32 to 3.51, P value 0.002. High-grade tumors have more than double the hazard rate compared to low-grade, strongly significant risk factor. Adjuvant radiation, HR equals 0.71. The point estimate suggests benefit, but the CI is 0.44 to 1.14. It crosses 1, not statistically significant in this model. We cannot conclude radiation independently improves survival after adjusting for other factors. Tumor size, HR equals 1.18 per centimeter. Each additional centimeter of tumor size is associated with 18% higher hazard. CI 1.05 to 1.33, significant. Now the crossing Kaplan-Meier curves for radiation at month 8. This is a red flag. The HR of 0.71 is averaged over the entire follow-up. But if curves cross at month 8, the radiation group may actually do worse early and better late, or vice versa. A single HR conceals this. The proportional hazards assumption may be violated for the radiation variable, and the results should be interpreted with caution, ideally with a time-varying analysis or separate early and late HRs. Key lesson: always look at the KM curves alongside the Cox table. A non-significant HR and crossing curves together should make you think carefully about what's really happening with radiation in this population. Sum it up. Cox regression is the natural extension of both Kaplan-Meier analysis and logistic regression. It handles time-to-event outcomes with multiple covariates. The output is adjusted hazard ratios that tell you the independent association of each factor with the rate of events over time. The critical habit: Always check the proportional hazards assumption by looking at the KM curves. A single HR from a model with crossing curves can be seriously misleading. And keep your OR versus HR versus RR table in mind whenever you pick up a survival or outcome paper. Identify the model first, then interpret the number correctly.